The few, the proud. I'm noticing that I'm not the only one who's getting very tired of all these Zoom meetings. As the end of the semester approaches, more and more people are using the YouTube videos instead of chiming in live so they can get right to the heart of whatever it is they want to learn.
You could become the next YouTube celebrity, though.
Yeah, right. I got to say, it's interesting because, you know, like your avatar just flashed on the screen just because you made a noise. And because of that kind of thing, I've been a little reluctant to even put these recordings on YouTube. I mean, you guys, you know, you deserve your privacy and so on, and you haven't signed waivers. So it's actually, I set it up so it's actually hard to find these videos unless you were given the link in advance. Nonetheless, there are people that somehow have some bots that are crawling over YouTube, because I've gotten several emails that said stuff like, wow, that's fantastic comment, fantastic content, follow my YouTube link or something. And it's obviously a bot that's not looking at anything, because I can't imagine anyone looks at Green's theorem and says, wow, that's really fascinating. Mathematicians, yes, but. All right. So before we get started today, I do want to clarify our timetable. This will be the end of this week is the last week of the classes. So we'll just meet today and on Friday as a group. And then next week already is the final exams. Our final exam will start. Let's see, I think I told you guys this last time. I'm going to have the final exam start on Wednesday. That's just a week from today. So here, I already sketched this out on a calendar. Is that legible? So we're already done with a portion of this week, but we'll have class today, a regular class, and then on Friday, it will be a regular class on Friday as well, although depending on how far we get today, we may be able to just run a little bit of new material on Friday, and then I can use the rest of the class on Friday for a review. Our exam will start on Wednesday morning, a week from today at 9 o'clock in the morning. That's when I'll make it available, and you'll have until 10 o'clock at night on Saturday the 16th. So the free response questions, you'll be able to use all of that time to work on them. And the quest ones, you can pick any time window you want in that long period, and I guess it'll be like 4 hours or something that I'm going to set the timer on quest. So, you know, you can already be starting to think when your other exams are and when you think you're going to be able to work your best on the quest portion. I did notice on the midterm exam, an awful lot of you were turning in your free response questions right near the end, which isn't a problem. I mean, in fact, I would encourage you to not rush on your answer in case you get a better idea a day later. But at the same time, I don't want you rushing in at 9:59, because then you might have equipment failure or something. So really, that's it. You guys will just pick up and return your final exam. It'll all be online. You'll meet with me today and again on Friday. There's no other scheduled class activities, although I did put in office hours. I'll have them go from like 11 until 1 on this Monday. I'll just for sure be here. And if you guys need to meet me at another time besides that, just let me know. I'll try to check my email and see which things I can schedule. On behalf of parents everywhere, I do want to alert you to the fact that Sunday, May 10th, is Mother's Day. So if it would make your mom happy for you to be doing your math homework, then do your math homework on that day. Otherwise, don't. Whatever mother figure you have available to you, just do something nice. Okay, so comments or questions on the timetable for the rest of the next 2 weeks?
I just had a quick one.
Certainly.
I know beforehand the exam was, I believe, scheduled for Tuesday or Wednesday, 9 to noon.
Yes.
So this final will be available for several days.
Yes. So you have way more time than you would ordinarily have had. Well, just for the free response portion, that should be way more time than you should need. I can't imagine you guys are going to be spending that's almost 4 full days just working on a few free response questions. But I did that in part because I know some people are on different time zones, and I don't want to hold them to having to meet at precisely the same time that we would have met. But I know some people do want to, I mean, they had already kind of planned how they were going to take their finals. They chose their courses perhaps with the intention of having finals spread out in a certain way, and you still have that opportunity for yourselves. I don't remember, you guys had your exam scheduled for Wednesday? I don't remember. But anyway, you can still take it at the time that it was made available to you before. I'm just giving you more options. Okay, anything else I should say about this planned schedule here? All right, then next, how about if I ask you about the homework? The homework, I believe, is due on Friday night, certainly not tonight. So I don't know how much you guys have started it. I hope you've done a bunch of the problems. Are there any ones on the homework that you want to ask me about? All right, well, some of them people have been asking me. They are about things like Stokes' theorem. So today I want to go through, I basically just described the outlines of Stokes' theorem last time. So I want to fill out all the details on that theorem today. It is a very cool theorem. Well, the whole chapter is just filled with cool theorems. There's one more cool theorem that we'll do after Stokes' theorem, and that's called Gauss's divergence theorem. And I want to at least get it stated today. I don't know if we'll have time to go through all the examples, but those will be the theorems. It's basically you had the fundamental theorem of calculus and the fundamental theorem for line integrals. You had Green's theorem, you've had Stokes' theorem, and then we'll have Gauss's divergence theorem. They are actually all of a pattern. The general pattern is called Stokes' theorem, but for our class, it's sufficient to remember these specific cases. All right, so let's have a statement of Stokes' theorem first. Here it is. So Stokes' theorem, like the other theorems in this chapter, merely asserts that two integrals are equal. It doesn't tell you why you would care or what you're going to do with them, but it says that two integrals will be equal. But they are integrals of different dimensions in the sense that this one on the left-hand side is a line integral. You'll have a curve on this side, and the one on this side is a surface integral. S will stand for a surface. So it's weird that those kinds of integrals can give you the same number. Another point that I do need to make clear, somebody was asking me in office hours, is that these things can be for fairly general situations. What you see written on the left-hand side is a completely general vector field in three-dimensional space. No constraints are necessary at all in order to get Stokes' theorem. And on the other side here, we have a surface that is a completely general surface that can float around in three-dimensional space. I mean, when I say general, there are some kind of technical constraints, and I'll mention a couple of them. Mathematicians would want it, I mean, like every theorem, there's technical conditions that you have to make sure are true, but the other conditions have to do with things like, oh, this vector field is supposed to be differentiable, continuously differentiable, the surface is supposed to be a smooth two-dimensional manifold, whatever. But I won't hold you guys to those formalities in this class. You'll have basically any vector field on the left-hand side. Now, on the right-hand side, you have to have an integrand there as well, and when you compute surface integrals, the kinds that have a dot in there, you know you're supposed to have a vector field in this spot, and I do, but this one is not a completely general vector field, and in fact, this one, it has to be the curl of the vector field you have on the left. And calculating the curl, as you know, that involves taking a lot of partial derivatives. So just In one word, I might describe this thing on the right-hand side as being the derivative of the vector field you have on the left. So f itself is completely arbitrary, but the vector field on the right-hand side is not. And in the same way, yeah, it's a line integral and a surface integral. The surface is really completely arbitrary. For your purposes, you can put any surface here, but you'll have a curve on the left-hand side, but it's not completely general. The curve that you have here has to be the boundary of the surface that you have on this side. And we've talked about this partial derivative symbol serving for that kind of a role. When you have a surface, more precisely an oriented surface, then this boundary symbol means that you'll get the curve that's at the boundary of your surface. So I do want to clarify what the boundary means. You need to envision a little bug that's walking across this surface. And, well, you know, you could, if you've ever watched a bug crawl in your skin, they managed to do it, and they change their directions apparently at random, and they don't care, they're just walking. The boundary of the surface is the place where the bug would have to be careful of which direction it walks, because if it tries to go in a certain direction, it would run out of the ability to have a surface to walk on. I mean, if you envision the thing sort of floating in space, then the boundary becomes the place where the bug would fall off. So the classic example would be if S is a disk, then the boundary of that disk would be the circle around the outside. But this circle can be kind of bent. You can pop it up a little bit, and you get, you know, a kind of a curve, a curved surface. In fact, at perhaps its most extreme amount of popping up, your disk would turn into a hemisphere. And so it's, say, the northern hemisphere on the globe, and then the boundary would be the circle that's at the equator. So that's the boundary of the surface. That's the limiting edge of where you can't walk any further, at least not if you try to walk in the southern direction along the northern hemisphere, then if you try to walk south, you'll just fall off. That same equator is also the boundary of the southern hemisphere on the globe. In fact, the two hemispheres come together along the boundary. So that, generally speaking, that's what this boundary of a surface means. It's the edge of where the bug can walk. All right, so that's the setting of Stokes' theorem. Give me a completely general surface and a completely general vector field, then you've given me half of the ingredients that I need to compute the two integrals. On the left-hand side, I need to know a curve to integrate that vector field on, and the answer is you're supposed to use the boundary of the surface. And on the right-hand side, I'm still missing what vector field am I supposed to be integrating along the surface, and the answer is you're supposed to use the curl of the vector field that was on the left. To kind of reinforce the pattern of the theorems in this chapter, oh, I'm sorry, I'm pointing to stuff you can't see. To reinforce the pattern of the theorems in this chapter, let me compare all of this to the fundamental theorem of calculus, which was also a mix of two different dimensions of integrals. On the right-hand side, you have an integral, a one-dimensional integral. You're integrating a function of one variable over an interval in R1. And on the left-hand side, it's actually a zero-dimensional integral. Remember, that's the one where you keep evaluating a function at points where you chop up a set into a smaller sets, and you evaluate the function on side each piece, and you simply multiply by the count of how many points were in each piece. And if you chop this finite set of points finely enough, then each one of the little pieces you chop into will just have one point in it. So you're just adding the function, sorry, you're evaluating the function at some points, and you're adding the values. Of course, the intervals in the real number line have a preferred direction. You go from left to right, so that's an orientation on that interval, a direction of travel on the interval, and that gives you an orientation on that finite set of points. Some of them are listed with a plus sign and some with a minus sign. Specifically, this interval has just 2 points on its boundary. The boundary of an interval is just 2 points, and we consider one of the larger point, the point that's further to the right, is given the plus sign, and the one that's off to the left is given the minus sign. And then you're adding and subtracting the values of this function at 2 points. To say it a little bit differently, you can use the fundamental theorem of calculus if you write your integral in the Calc 1 notation with two numbers in those two spots. And as you know, you don't always have to put the smaller number at the bottom and the bigger number at the top. And nonetheless, the fundamental theorem of calculus still lets you evaluate this integral by simply evaluating some function at the two endpoints, but it's the number that was written out at the top that gets the plus sign and the one that was written on the bottom that gets the minus sign. And that's true whether you've got the numbers, whether you've chosen this interval to be oriented in the usual way or in the reverse way. You can pick whatever orientation you want for the interval, either go that way or that way. And correspondingly, you get an orientation on that boundary, which only consists of 2 points. So we do have to be mindful. Go ahead.
Very quickly, could you read out the bottom line? It's a little blurry.
Yes, thank you for telling me, because everything
Yeah,
is
the resolution today is really low. It's
worse
really
than usual, huh? Sorry, guys, I just really don't know why this isn't working better for you. So the integral over here, so at the very bottom of this page is just it's a dotted line drawing your attention to the region of integration on the two integrals, and up here was another dotted line connecting the integrand on the two sides. You could have any function you want as the integrand on the left, in the same way that I said you could put any vector field you want as the integrand on the left, and you could have any interval you want on the right in Calc 1, in the same way that you can have any surface that you want in Stokes' theorem. But of course,
so that would be the same as dx at the bottom? Do those both, so is that ds at top and dx on the bottom?
yeah, I wrote ds over here because that's the way the book writes the surface integrals. I mean, you know that this is just one of the notations that we have for surface integrals. Another one that we've used is that you should be integrating curl of f dotted with a normal vector, and then I would put a dA over here. We write dA for surfaces because the way we measure the size of a piece of our surface is by measuring its area. And likewise, I might write this, if I were teaching Calc 1 today, I might write this as a dL, because the way we measure the size of a piece of an interval is to measure its length. So don't get too hung up on the notation that's used for these differentials, because people do vary in their choice of notation. But do remember that the differential is always there to remind you that you're evaluating some scalar valued function at different points inside your set, and then multiplying the value of that function times the size, length, or area of whatever chunk of your set that you divided this into. So, I mean, you guys remember how to compute integrals in Calc 1. I don't want to belabor this point too much. I just wanted you to see the parallels where you have an arbitrary function on one side and an arbitrary interval on the other side. But then the region, your set that you're integrating on the left-hand side needs to be the boundary of that interval. So that's just 2 points, the left point and the right point, or the upper limit and the lower limit. And you have to have a function to integrate on the right-hand side as well. And the function that you're integrating on the right-hand side is some kind of a derivative of the function you have on the left-hand side. So you guys in Calc 1 always saw that the way you were going to use the fundamental theorem of calculus was to start on the right. You were given an interval, and you knew you could use any interval in this theorem. And then you were given a function, and you knew that you were only supposed to use the fundamental theorem of calculus when you were integrating the derivative of something else. And so you always spent all of your time staring at your integrand, asking yourself, what the heck is the antiderivative of my function? Because that's what the capital F will be. The integrand that you were given is supposed to be the derivative. That's a little derivative symbol. It's the function you're integrating is the derivative of something that's on the other side. So you always started here, looked for an antiderivative, and then, well, you evaluated the zero-dimensional integral, which meant simply plugging in the two endpoints into capital F and adding and subtracting. You can do the same thing in Stokes' theorem. You could start with a surface integral, and say, well, all right, I will look, I've got a vector field in this spot. I will figure out what vector field, my vector field is the curl of, and then I'll jump over here to this side and I'll perform this line integral over the boundary of my surface. That's more work than it was in the fundamental theorem of calculus, because here the boundary was just 2 points, and here the boundary is going to be a curve. But worse than that, it isn't always true that when I give you a vector field on this side, that it even is a curl of something else. Not every vector field is a curl of another vector field. In the Calc 1 setting, it is true that every function of one variable is the derivative of something, but we can't always do it in this case. So you don't always use Stokes' theorem by going from this right-hand side to the left-hand side. Sometimes the interesting applications of Stokes' theorem go the other way, where you've got something on the left-hand side and you're going to rewrite it as something on the right-hand side. So I'll come to those special cases in just a moment, but let me ask you guys to clarify for me. Let me ask you if there's anything you want me to clarify for you about what the statement of Stokes' theorem is. You need to get the general framework of what these two intervals are going to be like. All right, so that's the framework for Stokes' theorem. So now what I want to do is to show you some cool special cases, and most of them, but not all, most of them will be like the cool special cases we had for Green's theorem. And then I will actually work out an example of Stokes' theorem where I'll just compute the two intervals on the two sides, just to really drive home what are the two types of intervals that we're looking at. All right, here we go. So special cases. Number one right away is you got to see that Stokes' theorem is actually subsuming Green's theorem. Stokes' theorem is all about surfaces that float in three-dimensional space, but they might drift all the way down to being in the xy plane. There's no reason that you can't use Stokes' theorem if capital S just happens to be a little rectangle in the xy plane, or a disk in the xy plane, or whatever. You can use Stokes' theorem even if you're in the xy plane in the first place. And furthermore, there's nothing to stop you from using Stokes' theorem in the case where your vector field is really just from R2 to R2. Remember, after we talked about Green's theorem, I said, sometimes if you have a vector field from R2 to R2, if you just tack on a 0 at the end, you'll get a vector field that goes from R3 to R3. Every point x, y, z would give you a vector field, something, comma, 0. So if you're in that special situation, so that's obviously both S is very specialized and F is very specialized. But in that case, Stokes' theorem still applies. And if you read what Stokes' theorem is saying, you say, oh, that's really just Green's theorem. So since Stokes' theorem subsumes Green's theorem, you shouldn't be surprised when I give you these special cases that are actually kind of useful. So one of them comes in the special case where your vector field happens to be the gradient of some scalar valued function. So not every vector field works that way. We did have a test for when that happens, namely you compute the curl of your vector field and look to see if you get the 0 vector field. This is one of those cases where the mnemonic of writing these symbols instead of CURL, this is a nice mnemonic because you remember that the cross product of any vector is equal to 0. And of course, this gradient is not really a vector. We kind of write it in vector notation, but anyway, it happens to be true that the curl of the gradient of a scalar field will always be the 0 vector field. And if that's the case, then this vector field on the right-hand side of Stokes' theorem is going to be the 0 vector field. And you're supposed to take that vector field and take the dot product with all these little normal vectors. But of course, you're just going to get a 0 as the scalar valued function to integrate on the surface. And of course, that integral will be a 0. So this is one of the cases when Stokes' theorem gives you a very nice, pretty result that some line integrals will just come out to be a 0. Of course, it's only applicable if the vector field is special. The vector field has to be a gradient, and not every vector field is. So don't jump the gun on this. And moreover, the curve C also has to be special because it has to be the boundary of a surface. Now, one thing that's automatically true is that that's going to force the curve C to be a closed curve. So this particular application of Stokes' theorem isn't going to help you evaluate line integrals that don't involve a closed curve. Anytime you take a curve that really is the boundary of a surface, that curve will itself have no endpoints. I mean, just think about this. I have here the top half of my glasses case is a surface. And its boundary is the set of places where that little bug might wander around and then realize that it has to stop because at least in one of the directions of motion, it can't continue any further. And that boundary will then be a curve. It has little bumps and wiggles in it, but the entirety of the curve, it will keep going and going. I mean, it comes back to where you started. So there's no boundary to this, to the boundary curve itself. The curve itself that's at the boundary of the surface doesn't have its own boundary. It's always a closed curve. It begins and ends. No matter how you choose to start walking on it, you're going to have to come back to where you started. I will say this, every curve that is the boundary of a surface will be the boundary of other surfaces too. So like a simple circle is obviously the boundary of this disk on the inside, but I've already talked to you about how it can be the boundary of an upper hemisphere, or for that matter, it could be the boundary of a lower hemisphere. They can all have that same circle as a boundary. You will always, in fact, have an infinite number of surfaces. Imagine making any surface that has your curve C as its boundary, and then make that as a flexible membrane of some sort that can vibrate back and forth, like the membrane in a loudspeaker. Then at every moment, that surface will have a shape. The shape will change, but the boundary won't. I mean, it's actually very interesting to take a drum head. You nail the drum head around the boundary, so the boundary never moves, but then when you tap on the drum head, it actually vibrates up and down in a certain pattern. And the drummers make use of the different types of patterns to make the thing vibrate in different ways. They're not thinking about this as they do it, of course, but it is true. You can get these different waveforms, these different shapes of how the drum head will vibrate depending on how you strike it. So the curve doesn't change, the boundary doesn't change, but the surface changes. I will also point out for the mathematician-minded people in the audience that the converse isn't always true. If I give you a closed curve, it isn't necessarily the boundary of a surface. That will be true for all the closed curves that I give you guys in exercises, but have a look at this knot. So there's a branch of math called knot theory, and what they study is these closed curves that sit inside three-dimensional space, and some of which are boundaries of surfaces, but others are not. So this particular knot is called a trefoil. It's supposed to be drawn continuously, but I made little breaks in it so you can see the places where the curve crosses on top of itself or tries to pass under itself. So that would be a knot, that would be a closed curve, but it's not the boundary of any surface. So I'm going to use, for us in this class, I'll use the phrase closed curve to mean, it's a synonym of saying that my curve is the boundary of a surface, but mathematically that's not quite true. So be aware that I'm being a little glib when I give you the theorems that we will be using. All right, so sure, Stokes' theorem is telling us that line integrals will be 0, but only under two very tight constraints. One is your vector field has to be a gradient, and number two is your curve has to be closed. It has to be a boundary. You can relax the latter constraint in the same way that we did for Green's theorem. If you want, as long as you keep this hypothesis that your vector field is the gradient of something else, then what Stokes' theorem tells you is that you can evaluate the line integral of a particular vector field along two different paths, and you'll get the same answer as long as the two paths have the same starting point and the same ending point. It doesn't matter how you get from A to B. Doesn't matter which path you use, you'll get the same value for the line integral. And the reason that that's a consequence of what I wrote up here is just by saying, well, you could make this closed curve C by simply traversing the curve C1 first, and then taking curve C2 backwards. Then that would make a closed curve because you would have come back to the point A. And the sum of those two integrals, of this one and then the other one going backwards, that's the same as the difference between the two line integrals that you see here, because this one is you get the negative if you go backwards. And on the other hand, when you do add those two line integrals up, what you will get, the situation you'll be in will be exactly this one here. You'll now be integrating over a closed curve, and so the difference between these two integrals would have to be 0. So in fact, we've seen this result before. In fact, we've already talked about exactly how to compute what this line integral is. It's simply the difference in the values of this function little f at the 2 points that are at the ends of the curve. From a physics point of view, you're saying if you have a force field that is derived from a potential energy function, then to figure out the amount of work that you have to do, you simply subtract the amount of potential energy at the beginning from the potential energy at the end. So you're used to this maybe for physical reasons, but it's a mathematical statement as well. All right, but these are still special cases. Even here, where I'm allowing you to use non-closed curves, I still have to assume that f is a gradient vector field. If you don't have a gradient vector field, if you just have a general vector field, and again, any curve, it doesn't have to be a closed curve now, I can still say something. And it starts off looking like the last one. It says, I don't care what vector field you have to integrate, and I don't really care what path you use. As long as you start at the same point and ending at the same point, you'll get the same integral. If you do have to make a correction, though. The correction term is you have to add in the rest of what the right-hand side of Stokes' theorem would tell you to add in. Remember, the difference between the left and the right sides is the integral of this vector field, f dot ds, over the closed curve that goes along curve C1 and then back along curve C2. So according to the original statement of Stokes' theorem, that's now an integral of f over a closed curve. Write that closed curve as the boundary of something, and then Stokes' theorem tells you how to evaluate that integral as a surface integral. So figure out a surface that's bounded on one side by C1 and on the other side by C2. And on that surface, just integrate this, the curl of f dotted with ds, or this time I wrote it as curl of f dotted with the choice of unit normal. That's the scalar value function that you integrate over this surface. So I do want to stress one thing. You get to pick which surface you choose that's going to be between the two curves, C1 and C2. What you can't pick arbitrarily is this unit normal vector, the n that shows up. We've talked about how to not have to have a unit normal and stuff like that, but what's also true is that every time you try to compute a surface integral, you have to decide which way you're going to consider to be the positive direction on your normal vectors. And I did mention to you guys last time that the choice of the normal vector on the surface integral side of Stokes' theorem has to match the choice of how you parameterized your closed curve on the line integral side. So if you have already got the curve C1 and C2 parameterized, you have to follow the arrows on C1 and go against the arrows on C2. And that is supposed to tell you how you're going to walk around the boundary of this surface. And remember that you're supposed to be walking with your left hand dragging around the surface and your head pointing up. So try following this surface and see if your left hand is following along on the inside of the surface. Follow along the curve and see if the left hand touches the surface. If your head is up, then you've chosen the right normal vector. But if your head is pointing in the opposite direction of the normal vector, then you've got the wrong one here. You have to switch to the opposite one. Anyway, that's a lot of words just for picking a plus or minus sign. But I want you to see that Stokes' theorem in this form can be very useful. It lets you rewrite any line integral. Give me any path and any vector field. If I don't like to compute that line integral, I have an alternative for a different way to do it. I have to integrate exactly the same vector field, but I can choose a different path that goes from A to B if I like a different path better. I will have to put in a correction term, but that correction term will not be a line integral, it's a surface integral. And there's a variety of reasons why this might be simple, like maybe this gradient, this curl turns out to be a constant or something like that. So the applications will vary, but this is one of the things that you can do that comes out of Stokes' theorem. It's a special case of Stokes' theorem. And like I said at the beginning, all of these applications that I've given you so far, all these special cases are really very much like things that we've said about Green's theorem. Because in fact, Green's theorem is a special case of Stokes' theorem. But I got one more application for you, one more special case of Stokes' theorem that doesn't really have an analog in Green's theorem, and that's this. What happens if the surface you've chosen has no boundary? It has an empty boundary. And for an example, I might point to something like the sphere. I mean, a little bug that's walking on the surface of the sphere never has to fear that it has to stop and change its direction for fear of falling off. I'm assuming the bug is wearing anti-gravity boots here, but or another way to say it is if you think about the upper hemisphere as having a boundary, which is the equator, the lower hemisphere has a boundary, which is the same equator, and the two equators actually sort of cancel each other out. You've glued the two pieces together and given something that has no boundary left. Even if you were to do this in terms of integration, if you were to pick a unit normal vector on the whole sphere, like here I've started to draw little outward normal vectors at each point. If you use that orientation on the upper hemisphere, it will give you an orientation on the equator that would say you need to walk, let's see, this way around the equator. Whereas if you use the outward orientation on the lower hemisphere, and you try to walk in such a way that your left hand is dragging around the lower hemisphere, well, that's going to force you to walk the opposite way. And so in terms of integration, if you're going to use Stokes' theorem, the relevant integral around the equator would be that direction for being the boundary of the top half and the opposite direction for being the boundary of the bottom half. And so if you wanted to use Stokes' theorem to integrate over the entire sphere, then the corresponding line integral on the left-hand side of Stokes' theorem would be a zero. It would be plus and minus the same line integral. And that's the conclusion in general. If you have an empty boundary, if your surface has no boundary, then there's nothing to put on the left-hand side, or you could put something that cancels something else out on the left-hand side. So the left-hand side of your integral for sure is going to be a zero. And that's true anytime you're integrating over a surface that doesn't have a boundary of its own, assuming, of course, that you're using Stokes' theorem, which is to say, that's assuming that the vector field you're integrating is the curl of something. Now, the other theorem, the one more theorem that I hope to give you at the end of the class today, it's called Gauss's divergence theorem. That'll tell us something that we can say about a surface that has no boundary, no matter what the vector field is. So that will, in some sense, be more powerful than, well, at least in this special case. But this is a nice special case. And if you're trying to integrate a vector field, which happens to be the curl of a different vector field, then you will for sure get 0 if your set S has no boundary of its own. That can be a sphere. It can be a somewhat dimpled sphere. If you push it on the top, that doesn't change the fact that there's a boundary. You can start to stretch and pull like silly putty. You can make this thing into different shapes. But you can even have other surfaces that have no boundary that you can't get them from the sphere without ripping and gluing and other discontinuous operations. So this thing is called a torus, and you're supposed to envision a donut, by which I mean just the icing on the outside of the donut. Or it's an inner tube, so it's the rubber inner tube with just space on the inside. So that's another surface that has no boundary. And therefore, any integral of a curl of a vector field will be 0 on these two surfaces. All right, so those are some special cases of Stokes' theorem, little things that little like freebies that you get. In this case, you can think of this as a way of using Stokes' theorem. But anyway, Stokes' theorem says what it says. It says that the two integrals are equal, and how you use that is up to you. Now, I'm going to show you an actual application an actual check of Stokes' theorem. I'm going to integrate the two sides, and we'll see that I get the same number. But just a few little sidebars that I do want to point out. In Stokes' theorem, you do have to make sure that you've started off with, that the orientation you've chosen on the surface matches the orientation that you use on the curve. If you get them wrong, then you'll be off by a minus sign. Sort of implicit in that is that you have to have a surface that has an orientation. By orientation, I mean you have to have a way of picking out a normal vector at every single point on your surface. Most of the surfaces that you see have that property. There's always a way of picking out a normal vector on a surface, and then as you migrate from one point to the next on the surface, you might have to shift the direction of your vector a little bit just to keep it perpendicular to the surface, but you don't have to do any sudden dramatic changes of like turning things upside down. But the fact that you can do that on the surfaces that I give you is the fact that those surfaces are orientable. They're all orientable surfaces. There are non-orientable surfaces, and for those surfaces, you can't do any of this Stokes' theorem stuff. So I thought I would just show you that. A Möbius strip is something that you guys may have played with in grade school. You can see I've just got a very narrow sheet of paper here, a narrow strip of paper. And I've drawn attention to just the top edge of this piece of paper. You see it on the two sides of this piece of paper. And by the way, to keep the two sides separated, I've got a white side here and a gray-blue colored side over on the other side. Now, you can make a cylinder out of this by simply gluing together the two short edges. This would be a cylinder, and I can describe an orientation for you. I would say, hey, let's just pick out a little arrow that points out of the blue side everywhere. And then you would understand what that means. Even if it gets kind of twisted, you still understand what it means to be always pointing out of the blue side. And as you move from point to point along this cylinder, this shape, that little outwardly pointing normal will vary continuously. But a Möbius strip is a non-orientable surface. If I make a half twist in the paper before I glue it, then I now have a situation where it doesn't make sense to say, hey, the unit normal should always stick out of the blue side, because now that would mean that you have unit vectors that are pointing like the tip of this pen over here, and then suddenly they're pointing like the tip of this pen on that other side. And so we have a discontinuity in how this normal vector is pointing. And it's not just that the blue side is somehow wrong, it's just that there is no way to consistently pick a normal vector all the way around this surface and have the normal vector varying continuously as you go. It's impossible to do it. And therefore, it's impossible to ever make sense of any of these surface integrals over a Möbius strip. I mean, you know that this little dot in here, it implies a calculation the way I wrote it like this. You take the curl of f and you dot it with the choice of normal vector that you've made at each point. Well, if you can't pick out a normal vector everywhere, then you can't make any sense out of this integral at all. So Stokes' theorem does not even apply to a surface like the Möbius strip, okay? We don't need to know that in this class because I won't give you anything like this, but it's a question that kind of makes sense mathematically, is what could we say in the case of a Möbius strip? And well, the main issue is that it really doesn't make any sense to even talk about surface integrals if you can't talk about a unit normal. Anyway, it's just a little, oops, I've given you guys a few mathematician comments today. I know some of you guys are math majors, and when you go to take a topology course, these will be pieces of information that you need. All right, I promised you a calculation, and I haven't a whole lot of time left, so here's what I'm going to do. I'm going to kind of rip through these calculations, and then if you want the details, find the YouTube video later today and go at it slowly. So what I did is I took my own advice at the beginning that said you could choose any vector field on the left side and any surface on the right side, and Stokes' theorem will make it work. So here you go. I picked out a kind of a random vector field in R3. 3 unconnected functions of 3 variables. And I needed just some surface, and so I didn't want to make it too complicated. I just took the graph of this function of 2 variables, or take the portion of it that lies over the unit disk. So as it happens, this is the graph of this is a saddle surface, and we're looking at the portion of that saddle that lies over the unit disk. So if you cut out of the central, circular area on a saddle, what you'll get will be something that has the shape of a Pringle. All right, so that gives me the thing to be integrated on the left side of Stokes' theorem, gives me the set over which I'm integrating on the right side. I still need the other ingredients. I need to know what function or what vector field I'm going to integrate on the right side, and that's supposed to be the curl of this vector field. So here I go, I started computing the curl. And on the left-hand side, the missing ingredient is what set am I going to integrate over? And the answer is it's supposed to be the boundary of that set. So I want the boundary of the Pringle, which is to say it's the curve that is part of the graph of f but lies over the unit circle. And that's me trying to draw it there for you. So Stokes' theorem asserts that 2 integrals will be equal to each other, and I'm going to compute them separately. There's the left-hand side at the top of the paper. I'll do the right-hand side at the bottom. Okay, ready, set, go. To evaluate this line integral over here, it's a curve. I have to begin by parameterizing the curve. My curve in question was this one that went around the edge of the Pringle. I've already lost it. Here's the picture. So to parameterize that, I'll choose my x and y coordinates to just go around the circle. And then since I'm supposed to stay in the graph of the function, I let the z coordinate has to be 7 times x times y. There's your parameterization function. The values of the parameters you need are all the numbers from 0 to 2 pi. Then to evaluate the integral, I've changed my region of integration. I have to change my integrand by substituting away the x's and y's and z's. Well, that's going to be the x, there's your y, there's your z. And so since the thing I'm integrating is here, I'll get 2 times the y. I'm sorry, I'm doing the left-hand side. So this is the vector field I'm integrating. So 2x plus 3y is now 2x plus 3y, and so on and so forth. That's the function to be integrated. And the third step is to rewrite the differential. You know that you get that by multiplying the differential of t's by the velocity vector. So here I just differentiated my parameterization. This is phi prime of t in the 3 components. And then I just take the dot product of this long mess with this long mess, and I get a whole mess of trig-y things. The product of these two entries is here between the parentheses. The product here is in that set, and then the product of these two parts will actually have 4 components shown here. This actually goes kind of fast because, as you guys remember from Calc 1, when you integrate a product of trig functions over the interval from 0 to 2 pi, that interval actually turns out to be 0 as long as there's an odd exponent on either the sine or the cosine. So most of these terms drop out. I had only a few left to compute, so I took those coefficients times the integrals of either sine squared or sine to the 4th or cosine squared sine squared. I did them. Those are the values. And when you add up all the contributions, that's the value of your line integral. Okay? Nothing special here. Completely normal calculation of a line integral. Likewise for this one, nothing really special, but you're doing a surface integral now. You're integrating over the entirety of the Pringle. So you have to parameterize your surface, and that requires 2 parameters. And I'm using here what I would have called the cheater's parameterization. These are synonyms for x and y. So there's the z is f of xy. There's my parameterization. Here's my parameterization space. I have to do the same thing as always. You're going to rewrite your integral on the right by changing the region of integration. Now it's that disk. You have to change your integrand by substituting away the x's and y's and z's. That's going to be your x, that's going to be your y, that's going to be your z. And then you have to take the dot product. You have to rewrite your differential. You know that that's the part that has the tu cross tv in it. I've computed the derivative of capital T and found the cross product of the 2 columns. And when you compute the dot product, here is the scalar valued function that you're going to integrate over the unit disk. And since it's a unit disk, I switched to polar coordinates. And as before, there's a lot of triggy stuff in there. But most of those trig integrals vanish. And so the integral with respect to r is very easy. And then when I calculate the value, I get a number. Again, nothing interesting about this number or the method of calculation except for one thing, which is that it matches the line integral I had before. So, what I wanted you to see from those calculations was just a reminder of exactly what the 2 integrals on the 2 sides of Stokes' theorem mean. Now, I wanted to start Gauss's divergence theorem. I will just kind of read what it says here, but if you want to ask me questions about what I just did with Stokes' theorem before we leave that. I know I'm out of time, so. All right, if you have questions about Stokes' theorem, please drop into office hours today at 1 and at 3. And then on Friday, when we begin, I'll be giving you a similar discussion of Gauss's divergence theorem. You can see it's another one of these things that compares 2 integrals. This is a 3-dimensional integral over a 3-dimensional chunk of 3-dimensional space. And this one here is a surface integral of a function on a surface that floats around in 3-dimensional space. All right, guys, come in on Friday for the last class, and then start getting ready for next week's final.
Thanks, Dr. Wesson.
All righty, so we'll see you next time.